In the previous video, we solved the single source shortest path problem for graphs with non-negative edge weights using Dijkstra's algorithm. And we showed how this algorithm performs by going through an example. And now in this video, what we're going to do is analyze the complexity of Dijkstra's algorithm. Before analyzing the complexity of Dijkstra's algorithm, we must consider what data structures are used. And we know from the previous video that we used a heap, or more specifically a min heap, to perform Dijkstra's algorithm. And there are two situations where we manipulate the heap one way or another, and it no longer holds this property where its parent node is smaller than its two children node. And this is where we will have to perform a method called heapify to restore the integrity of this heap property. And the two situations we're going to talk about now are, the first one is when we make a DQ operation. And when we DQ an element from a tree, let's just consider an example. So let's consider this example of a min heap where we've got 1 as our first node, and then we would just have 2, 3, 4, 5, 6, and 7. And consider we DQ from the heap, and that means 1 will come off, right? And so we no longer have 1 in this node, and you can see that we no longer hold this heap property where its parent is smaller than the two children nodes, as we do not have anything in this node. And so what we're going to have to do is perform heapify. And what this means is we're going to have to change our heap to restore this heap property. And so what we have to do in this case is we have to bring 2 up, because that's the next smallest element. So we're going to have to bring 2 up. And so now you can see that 2 is the smallest element, and we no longer have a value here. So for this smaller subtree, we can see that we do not have the heap property defined. So what we're going to have to do is bring our next smallest element up, which is 4. And 4 comes up. And now you can see we don't have a node here, and it doesn't have any children, so we can get rid of this. And you can see now that we have restored the heap property in this balanced binary tree, or this heap, as we have a parent that is always smaller than its two children. And another situation in which we have to perform heapify is when we either change or add a new element to the heap. And so let's consider the same example. So we'll draw that out again quickly. And consider we change one of these values. And we're going to consider the worst case here. And so we're going to change one of the leaves of this tree. So let's say we change our value 6 to 0. And so to maintain our heap property, we're going to consider first this subtree. And to maintain the heap property, remember our parent must be smaller than the children. So 3 and 0 must swap. So let's rub this out. And so 3 will come down and 0 will come up. And so now we got a parent that is smaller than the two children. And we can consider now the whole tree where the parent is not smaller than the two children. And so we're going to have to make a swap between 0 and 1. So we rub out that, and 0 will come up and 1 will come down. And we can just quickly check to see if our heap property is maintained throughout, and it looks like it is. So we have restored the heap property by performing heapify for this case where we have made a change operation. And now this leads into our discussion on the complexity of heapify. So in the worst case, you can see in both situations, we have to percolate throughout the entire height of the tree. And we know that the height of a balanced binary tree is log of n plus 1, where n is the number of nodes in our heap, or in our binary tree. And all these swap operations between adjacent nodes in the heap are all constant time operations. And so in the worst case, we have to consider log of n plus 1 constant time operations for heapify when we have to percolate through the entire height of the binary tree. And so the complexity of heapify in the worst case is going to be big O of log n plus 1, where n is the number of nodes in our heap. Now we can tighten this bound and show that log of n plus 1 is big O of just log n. And to be detailed as possible, we are going to prove this right now. So here we want to prove that log of n plus 1 is big O of just log of n. And so we have discussed these proofs in previous videos. So this will be a bit of a revision, and we always start by showing that there exists a C value that is an element of the reals greater than 0, and there also exists an n naught that is an element of the natural numbers. And for all n greater than equal to n naught, we have the following condition. So the following inequality, where we have log of n plus 1 is smaller or equal to our constant C times log of n. And we only need to prove this inequality for a given C and a given n naught value, which we can choose. So here, I'm going to choose something. Consider C equals 10 and n naught is equal to 2. So you can choose any value that works for this inequality. I'm going to choose these two values and prove it with C equals 10 and n naught equals 2. And then this will show that this log of n plus 1 is big O of log n. And so we can rewrite our statement above as just, we'll abbreviate a bit. For all n is greater and equal to n naught, which we said was 2, we have log of n plus 1 is smaller and equal to C, which we said was 10 log n. And now what I'm going to do is apply a couple of log laws. So this is equivalent to, for all n is greater than equal to 2, I'm going to leave this alone for now, and I'm going to apply a log law to this right hand side of our inequality. And instead of 10 log n, I'm going to rewrite this as log n to the power of 10. And this comes from the log law, which I'll write to the side here. If we have log of x to the power of a, we can rewrite this as a log x, or vice versa. So here you can bring the 10 to the front, or you can if you have the 10 at the front, you can bring it to the power of whatever's inside the log. And the reason I do this is for the purpose of the next line. And the next line, I'm going to apply another log law. And so this is equivalent to n is greater than or equal to 2. And what I'm going to do is bring this to the power, both these logs to the power of 2. Because remember, what you do to the left, you have to do to the right. So 2 to the power of log n plus 1 is smaller and equal to 2 to the power of log of n to the power of 10. Now the reason why I've written this line is because we can apply another log law now. And I'm going to write this to the side. So for example, if I have 2 to the power of log base 2 of, let's just say x, this is actually equal to x. So if we have a base to the power of a log with the same base, then this is just equal to whatever's inside the log. So in this case, x is inside the log, and this will just be equal to x. And in computer science, we can abbreviate, if we just have log base 2 of x, we can abbreviate this as log x. And in other areas of maths, this will be different. But for computer science, we can, whenever you see log of x, this is the same as log base 2 of x, just abbreviated. So now we can apply this log law to form our next line of working, which is going to be for all n is greater than or equal to 2. If we have a base to the power of a log with the same base, and remember by the abbreviation this is base 2 as well, we just get whatever's inside the log, which is just n plus 1 is smaller and equal to 2 to the power of log of base 2, which is equal to whatever's inside the log, which is n to the power of 10. And here you can see that a polynomial of degree 10 is obviously going to be greater than a linear function. And all we have to do now is write some general statement that clarifies this. So we can write something like the above inequality will always hold as any polynomial is trivially greater than a linear function. And it's always good to state our base case, which is for this n is greater than or equal to 2, our base case will be n equals 2. And just do a quick calculation. So 2 plus 1 is 3. And we need to show that this is smaller than n, which is 2 to the power of 10. 2 to the power of 10 is 1024. And 3 is smaller and equal to 1024, obviously holds. And we should also say that for n is greater than 2, so we said for n is 2, and now for n is greater than 2, the inequality will also hold. So that's the way I would write the explanation. There are other ways to say it, but I think this is enough to get the marks, especially for an exam situation. And now let's rub the side out here to make our final statements for this proof. And so we can say something like, therefore, log of n plus 1 is big O of log n. And then we can end our proof like that. So in conclusion, Heapify has a complexity in the worst case of big O of log n, where n is the number of nodes in our heap. So now with the complexity analysis of Heapify out of the way, we can now start to consider the complexity of Dijkstra's algorithm. To the left here, we have our example from the previous video, which we used to help us understand Dijkstra's algorithm, and the following information that came with it as we walk through the algorithm itself. So this was all from the previous video, but we're going to use it in this video to help us understand the complexity. Now, if you remember from the previous video, these red titles illustrate each iteration of the while loop. And the first line of that while loop was a dequeue operation from the heap, which we store the result in a variable u. And you can see our u values here within our iterations. And if you look carefully, we dequeue each vertex from the graph exactly one time. So we can see in our first iteration, we dequeued 0. Our second, we dequeued 2, then 4, then 1, and then finally 3. So we visit each vertex exactly once. And this is achieved by the dequeue operation. And remember that the dequeue operation is one of the two properties that will trigger heapify. And so we can start to analyze the complexity for this part of the algorithm. So we're going to have big O of, and we're going to do the magnitude of V representing the number of vertices in our graph. And we dequeue exactly V number of vertices from the graph, right? So each vertex is dequeued exactly once. And remember that dequeuing will trigger heapify, and the complexity of heapify will be log of the number of elements in our heap. And the number of elements in our heap is going to be the number of vertices as we build a heap with these vertices. So for the dequeue operation of Dijkstra's algorithm, we're going to have a complexity of V log V, where we dequeue exactly V elements from the heap. Now, continuing on into the algorithm, you can see that we reach the for each loop where we visit each neighbor for the currently dequeued vertex. Within this for each loop, there is an if statement, and when satisfied, we undergo a change operation, which again will trigger heapify. And so what we need to do is find out how many times we actually enter this if statement, which will determine how many times we undergo heapify from this change operation. And the way we do that is by looking at the amount of inequality calculations that we have made, because these calculations were all done within the if statement where we change the key values. And so before counting the number of inequality calculations we have actually done in this particular example, I want to go over one more concept, and that is the concept of an edge, right? The definition of an edge. And the way we define an edge on a graph is by listing the pair of vertices that are adjacent to each other or that are neighbors. Because if we know that pair of vertices are neighbors or adjacent, then that means that there is an edge between them. So suppose in a general case that V is a neighbor of U, then that means that if we draw V and we draw our vertex U, and we're saying that V is a neighbor of U, right? Then there must be an edge between them, right? And so this, by defining a pair of vertices that are adjacent to each other or that are neighbors, that will actually define the edge between them. So when we translate to this example here, when we actually go into this if statement, I want to see how many edges we actually check, right? So if you consider, for example, in our first iteration of the while loop, we're considering the neighbors of 0, right? Our vertex 0. And the neighbors that we actually undergo an inequality calculation is 0, 2 and 0, 4, right? So our edge 0, 2 is checked, and our edge 0, 4 is also checked. So we can tick them two edges out, right? And now in our second iteration, we undergo an inequality calculation on 3 and 4, which are the neighbors of 2. So if we consider our vertex 2, we consider the edge 2, 3, right? So 2, 3 is considered, where we do an inequality calculation and therefore a change operation, which will trigger heapify. And also we visit the neighbor 4 of 2. So we visit this edge here. And if we go into our third iteration, we visit our neighbor of 4, which is 1, right? So we check that edge there. And in our fourth iteration, we check our edge 1, 3. So we check this edge here. And then in our fifth iteration, we don't check any edges because every vertex is already dequeued from the heap. And so we never enter that if statement. In conclusion, you can see that we visit every edge exactly once where heapify is triggered from the change operation. And so we can write the complexity for this for each loop of the Dijkstra's algorithm. This will be big O of the number of edges, right, times, and for each edge we do a heapify operation, which again will be log V as discussed before. Now what I want to do is simplify this complexity a little bit, and we can do this by showing that the number of edges in a graph is actually big O of V squared. And we can show this by considering, in the worst case, a complete graph. And in a complete graph, we want to find the amount of ways that we can choose two vertices, which remember, two vertices define an edge, out of V vertices. So this is just a combination. We want to find V choose 2. Or in other words, we want to choose two vertices defining an edge out of V vertices, where V is the number of vertices in our graph. And by using our combination formula, this will become V factorial divided by 2 factorial times V take 2 factorial. So this is just a formula which you may have visited in high school, or at least in first year uni. And now we can do some simple factorial simplifications. And so we can rewrite V factorial as V times V take 1 times V take 2 factorial. And the reason why I wrote this down like so is because we can see that we have a V take 2 factorial on the top and bottom of the fraction. So these will cancel out. And so now we're left with V times V take 1 over 2 factorial. And 2 factorial is just 2 times 1, which is just 2. And if we expand this out, we get V squared take V over 2. And so here we've shown that the number of edges in a complete graph will be equal to V squared take V over 2, where V is the number of vertices in our graph. And so what I want to do now is I want to prove that V squared take V divided by 2 is actually big O of V squared. So now let's rub this out and leave some room to do this proof. So now continuing on with this proof, we first write our line where there exists a C that is an element of the reals greater than 0, and there exists an n naught that is an element of the natural numbers from 1, such that for all n greater and equal to n naught, the following inequality must hold. And that inequality is n squared take n divided by 2 is smaller and equal to C multiplied by n squared. So now what we have to do is find a constant C and n naught that will satisfy the following inequality, and that is sufficient enough to prove what we're required to prove. So we're going to consider C equals 1 and n naught. N naught equals 1 as well. So let's rewrite our inequality, and we get for all n is greater and equal to n naught, which is 1, n squared take n divided by 2 is smaller and equal to C, which was 1, so we can leave that out, times n squared. And now what I want to do is slowly do some algebra to manipulate this equation into something that we can trivially see that the inequality must always hold. So what I'm going to do first is multiply 2 to the other side. So we're going to have for all n is greater and equal to 1, we will have n squared take n is smaller than or equal to, multiplying 2 to the other side, we get 2n squared. And now what I want to do is take the n squared over to the right hand side. So we end up getting 2n squared take n squared, which is going to be 1n squared. So we can get rid of this 2. And now we're left with negative n is smaller than or equal to n squared. And the final line that I want to do is for all n greater than or equal to 1. I want to divide both sides of the equation by n. And so we're going to get negative n divided by n is negative 1. And that is smaller than or equal to n squared divided by n, which is going to be n. And now from this line, you can clearly see that this inequality must always hold for n is greater than or equal to 1. Because if we sub in from starting from 1, 1 will always be greater and equal to negative 1. And then going onwards to 2, 3, 4, etc., this will always be greater than negative 1. So this statement must always hold. So now what we can do is just write a brief paragraph just explaining this conclusion. So we can say something like, it is trivial that negative 1 is smaller than or equal to n for n is greater than or equal to 1 as n can never be negative. So this is something that you could say that will be sufficient enough to get the marks in an exam. And something that I always like doing as well is that we can state for the base case n equals 1. We get negative 1 is smaller than or equal to n, which is just 1. And that holds. And then we can also say for n is greater than 1, the inequality will also hold. And then finally, therefore, v squared take v over 2 is equal to big O of v squared. And that's our proof. So now let's rub this out and leave some room to do some final conclusions. So now we can change our complexity here to big O of, instead of the magnitude of e, the number of edges, we can make this into the number of vertices squared, multiplied by log of v. So now we have all the information to finally write the overall complexity of Dijkstra's algorithm. So the overall complexity will be big O of v log v from dequeuing v vertices. And we don't end there, we have to add the e log v, which we found that can be simplified into v squared log v to get everything in terms of the number of vertices of our graph. And that comes from a change operation for every edge of the graph. And so this is going to be our overall complexity of Dijkstra's algorithm. And the final thing that we need to do is just tighten this bound up a little bit, and we can show that v log v plus v squared log v is big O of just v squared log v. So let's rub this out to leave some room to do this final proof, and then we're going to be done with Dijkstra's complexity analysis. So to start our proof, let's rewrite that line. So if there exists a C that is an element of the reals greater than 0, and there also exists an n0 that is an element of the natural numbers from 1, where for all n greater than equal to n naught, we get n log n plus n squared log n from the left-hand side of our equation is smaller than equal to our constant c that we defined times n squared log n. And now we can just choose two arbitrary constants and prove that the inequality holds for these constants. So I'm going to choose c equals 10 and n naught is equal to 1 for this case. And we can rewrite our inequality now. So we get for all n is greater and equal to n naught, and n naught I said was 1. And we're just going to rewrite our inequality. The only thing we need to change is this c value, which we said was 10. And now what I want to do is do some algebra, 3, 2, 1. And now what I want to do is 3, 2, 1. And now we can manipulate this inequality, 3, 2, 1. And now we can manipulate this inequality to try get to a position where we can trivially see that the inequality will always hold for n is greater than equal to 1. So let's do some simple algebra. And the first thing what I want to do is factor out an n log n on the left-hand side. So let's do that. Where we're going to get n log n, and inside the brackets we'll get 1 plus n is smaller than equal to 10n squared log n. And now if I divide n log n, if I 3, 2, 1, and now if I divide both sides by n log n, we're going to get this n log n will disappear, and also an n log n will disappear. So we're just left with 10n on the right hand side of our inequality. So finally we're left with, for all n is greater than equal to 1, we're just left with 1 plus n is smaller and equal to 10n. And now we're in a position where we can obviously see that this inequality will always hold for n is greater than equal to 1, because we have 10 times some constant, and that will always be greater than just 1 plus that constant. So we can just write a small paragraph or sentence just writing this conclusion down. So we can write something like, this inequality will always hold as 10 multiplied by a constant will trivially always be greater than 1 added to that constant. If the constant is greater or equal to 1. And what I like to do is write in our base case. So our base case is going to be n equals 1, and write in our inequality. So 1 plus 1 is 2, is smaller than equal to 10 times 1, which is 10. And you can see that this holds, as 2 is always going to be smaller than 10. And then we can just say for n is greater than 1, the inequality will also hold. And so therefore, we can write in our proof, the magnitude of v log v plus v squared log v is equal to big O of v squared log v. And so to conclude, our final complexity of Dijkstra's algorithm is going to be big O of v squared log v. And so that concludes this video, and in the next video we're going to prove the correctness of Dijkstra's algorithm.